Well, good evening, everyone. I'm David James, and I'd like to welcome you to this Institution of Engineering and Technology Sussex Network talk. So now it's my great pleasure to introduce Nicolas Herzig. Nicolas is a lecturer in industrial automation, mechatronics, and control engineering in the School of Engineering and Informatics at the University of Sussex. Luckily, he lives in Crawley, so he didn't have to travel too far. But he's also a member of the Robotics and Mechatronics Systems Research Group. Nicolas received his PhD in control engineering from the Université de Lyon in 2016. Before moving to Sussex, Nicolas worked on projects for medical robotics at the University of Sheffield, Imperial College London and King's College London. He says his research interests are focused on the development of new technologies for robotic systems. And I think that's what we're going to hear a bit about tonight. So, please, Nicolas, over to you.
It's my great pleasure to be here today to present a bit of my research work. I'm currently a lecturer in mechatronics, automation and control at the University of Sussex. And I would like to thank the IET for the invitation and thank you for being here tonight. So today I will be talking about compliant robotics, and in particular I will try to focus on how to break the barriers between robots, humans and their environments. So basically I will start with a quick definition of what is compliance. And basically, compliance is the ability of an object to bend or deform. I often take as an analogy the simple spring. Okay, the spring is a mechanical element which, if I apply a force, the element will deform, will displace, and the compliance is actually the opposite of the stiffness. So it's the ratio between the displacement over the force. Okay, and basically it's used to describe the flexibility or the suppleness of a robot. So I take as an example those type of robots which I consider as stiff, so not compliant robots, which are classic industrial robots. You can see here probably in a production line for cars. And basically, those robots, you can see that they need to be protected with those fences where no human is allowed to cross there, except in a specific condition when the robots are basically stopped, because since those robots are very stiff, they may be dangerous and could harm anyone entering their workspace while they are moving. So I oppose those type of robots to this type of robot. So here we have a UR5, which is a universal robot. And basically it's called also a cobot for collaborative robot. And basically in its controller and in design, it's meant to be collaborative with humans. So basically here for this type of robot we find some control strategies that will allow users to apply a force while it's moving, and the robot will interact safely with the user. Additionally, we can see that here in the gripper we have what we call a soft gripper. Okay, so this gripper is made with elastic material, which will also bring some compliance to the robot. So you can see here to grab an empty can without crashing it. So basically, I'm working on compliant robotics, so I'm more on that side of the robotics. Now, to explain a bit how we can reach, how we can make a robot compliant, there are, I would say, two main approaches. The first one is basically using a mechanical approach. So in the design of the robot, we will either use some soft materials. So, as I was mentioning, soft robots, soft materials are robots that are made from elastic materials, elastomers, rubber silicone, those type of elements. So it will bring elastic body to the robot. We have another approach is using passive elements. So I gave the analogy to a spring earlier. So basically we can introduce some passive element. Here you can see some springs. The name of that device is called the remote center of compliance. And basically, by putting those springs in parallel, basically, if we try to guide the robot to assemble two parts, and those parts are not perfectly aligned, basically this compliance will take over and allow the alignment of the parts. Then another mechanical approach is designing what I call compliant mechanisms. And those mechanisms are generally composed of different elements. And here we have an example, it's called the MACEPA, which stands for Mechanically Adjustable Compliance and Controllable Equilibrium Position Actuator. It's really long, so MACEPA is fine. So we have three parts basically. The green one, which is attached to the base of the robot. And then here we have the robotic joint itself, and we will have two motors. So one that will basically position the red link here to a direction, and the second one that will basically tension a spring, okay? And basically the first one can give a general direction, where the second one attached by the spring element, if I apply an external disturbance to the robot, it will basically comply around the expected position that is given by the red part. So what it means is that with the second motor, I can adapt the stiffness, I can adapt the compliance in real time according to the condition. Do I want a very stiff joint, or do I want a compliant joint according to the scenario? And we can tune that with that second motor. So that's the mechanical approaches. Of course, I mentioned it a bit earlier. There are also possibility to work on the control strategy. How do I control my robot to make it compliant? And here are some examples of control strategies for robots that brings compliant behavior to the robot. And the main ones are stiffness controller, impedance controller, or hybrid force position. And basically they rely generally on the measurement of the disturbance, so measurement of the external force applied by the environment or by the user, and then it's implemented in a control strategy to instead of being very accurate on the reference position we aim to have, we take into account that interaction to move the robot and basically comply. So if I have to compare all these methods very quickly, of course it's a bit more complicated than that, but I try to simplify a bit the context. So the control strategy, what is interesting is needs generally a minimum hardware modification, meaning that except adding possibly some few sensors, we don't need necessarily to redesign the whole robot. Okay, so it's quite interesting in that sense. One of the limits is what I would say the bandwidth is, since most of those strategies rely on the fact that we need to sense the disturbance and let the controller react. They don't necessarily behave super well when the interaction is with a really high frequency or any shock, for example. Sometimes the impact with the robot is already done, and then the controller starts trying to add the compliance, but it's not necessarily instant. So the other approach based on mechanisms or variable stiffness actuator, they are generally quite simple to control because they're built in such a way that there is one element dealing with the position we try to reach, and another element that will control directly the stiffness. So it's quite simple to implement. However, they generally get a very limited range of stiffness variation. So the compliance we can reach is generally always in the same range due to the fact that they rely on passive elements. So finally, we have the last type of robot, which are soft robots, where in that case the whole body is compliant. So it's very interesting because everything in the robot is compliant, but we have some control issues in the sense that since the robot is now soft, most of the tools we have designed in robotics the last 30 years are basically not necessarily applicable because the basic in robotics is generally to rely on the fact that a robot got rigid links. So you can imagine that the non-linearity introduced by those type of materials kind of complexify the study. So I believe that compliance is really the key to break the barriers between the robot and the humans, or the robot and the environment. And I will try to illustrate that through different examples taken from my research. And in particular, I would like you to appreciate how compliance can enhance actuation, in the sense that it will make the thing more robust, so robust to a disturbance, to unpredicted condition, or adaptable. That's the same idea, that it will make the robots adapt to uncertain environments. And the second thing is that it also it can improve the perception. So the perception, I mean by perception the sensing of the robot. And since compliance is actually a kind of element that can filter the mechanical signal, let's say, it can play a role where using compliance we can basically filter the unnecessary the mechanical signal that we don't need, and condition the perception of the robot to extract really the information that matters. So unfortunately I won't have the time to cover all these examples, and today I will be focusing on the perception with the palpation probe, and for the actuation part I will talk about this three a bit more in detail. So I propose to first start with the palpation probe, and to give a bit of context about this probe. It's basically a work that I've been doing while I was at Imperial College, and it was before the big coronavirus pandemic, but at that time we had Ebola in mind, which is a really contagious disease, and we were thinking that maybe having a robot that could perform palpation to the patient would be interesting, because like that a GP practitioner could be in a safe place, sending a robot to perform the palpation. The robot would send back the data to the GP, and the GP could evaluate the state of the patient remotely. So to do so, we work on the palpation probe to analyze the condition of the patient, and an active phantom. A phantom, we refer to a phantom where for basically kind of advanced mannequin that reproduce a patient condition. Okay, so basically, yeah, the idea was to develop those two so we can perform a remote palpation. I personally mainly focus on that part, but I will talk a little bit of the two. So basically, there was some context already when I started working on a project, and it's been done by a student at King's College. And basically, that what he studied is basically when we try to assess a property, such as evaluating the weight of an object, or when a practitioner is performing abdominal palpation. Basically, we rarely do those type of tasks statically. So if you look, when we ask generally someone to evaluate the weight of an object, that person won't be just grabbing and say, okay, I think it's 20-30 grams. Generally, people are kind of shaking the object. And we were trying to figure out why that, why we need that motion. And one hypothesis we developed is by measuring the muscle activity of antagonistic muscles in the arm. Basically, we look that at some point when we do those type of motion, we contract both muscles. Okay, and those forearm muscles control basically the motion of the fingers and the wrist, but also their compliance. Okay, so basically, if I contract both antagonistic muscle at the same time, I will make my fingers very stiff. But if I relax, they are compliant. Okay, and so we looked at how that compliance is evolving during a task of palpation or a task of evaluating the weight of an object, and we noticed that compliance is changing with time. So the hypothesis we formulated is probably that compliance can help getting more information during those operations. So to test that a bit further, I decided to design a new palpation probe that could basically change stiffness in real time to perform palpation. So here is the model of the probe, and basically you can see that there are some rigid parts, 3D printed parts here, in which we have in the middle here a carbon fiber rod that can bend. It's the same thing that is used in some tents or things like that. And what the way it works is simply the principle of a cantilever. If the cantilever is very long, it's easy to bend at the end. Now if I shorten the length of the beam, it becomes very stiff. So basically by changing the length of what I call the active length of the cantilever beam here, we can change the stiffness at the joint level of the finger. So we studied a bit how that stiffness is changing, how the compliance is changing according to the length, etc. And then I started to investigate the palpation aspect. Okay, so here we have some rubber silicone material, so which is quite soft. We try to match the stiffness of soft tissues during the palpation, and inside that silicone I have placed some plastic beads which represent let's say some cancer tissues that would be stiffer than the rest. And the idea is, can we first detect those type of stiff inclusion, and can we even more predict the depth, how deep are those nodules. And basically, I studied two types of sweep for the finger. So the first one, using the probe I didn't mention, but is equipped with two sensors. One here, which is a tactile sensor, but will basically measure what happens at the skin level when we palpate. So it's using capacitive sensors to measure the pressure contact at the skin level. And here we have a force sensor, a load cell, that will measure the normal force here, and that load cell represents more the information we get from our tendons when we try to palpate, what we call the kinesthetic sensing of the body. So using those, I basically studied what we could get from those two sensing for different stiffness. So basically we swap laterally with the finger fully in contact with the tissue, and slide, and we can see that while sliding, we can notice a kind of peak of force when the probe reach over the nodule. Okay, so it means that using that peak information here, I can estimate when during the sweep that nodule was detected. And with the tactile information, maybe I can locate where in the finger was that nodule. Okay, so by correlating the two information, I can localize where the nodule was. The second type of sweep I've been investigating is what I call the longitudinal sweep. So this time we sweep the finger in this direction. And similarly, I tested with different depth of nodule. I tested with different stiffness every time, and we can see that here, so the range of value is the same, but the peak is slightly easier to detect. So after combining all the results, this is what we obtained. And I know that those figures might be a bit scary at the first the first time, but basically what it shows in summary is that for the lateral sweep, we have here a gap. So those are probability distributions, but we can see that the probability distribution are separated between so for the force peak when there is no nodule and when there are nodules. Okay, so what it means is that for the lateral sweep, we can detect when there is a nodule and when there is no nodule, but it's extremely difficult to detect, to estimate the depth. You can see that for different depth, they are all kind of merged, and it's not really possible to detect the depth of the nodule. However, if I look at the longitudinal sweep, we can see that this time the case where there is no nodule is quite close to the case where the nodule depth is around 8 millimeters, but we can distinguish each depth independently. And moreover, the role of the stiffness, so the compliance of the finger, will play a role. You can see that the distance between two distributions of some depth is changing with the stiffness. It means that if I look at, for example, for this stiffness, here, the force peak measured when the nodule is at 8 or at 6 millimeters are kind of overlapping. So here, that's probably not the best stiffness to distinguish between those two depths. Okay, but at contrario, for the distance between 4 millimeters and 2 millimeters is quite large. So it means that here, depending on the force I will be measuring, I will be more likely to decide if it is 2 millimeters or 4 millimeters. So we build a tool called the information gain, which measure for each stiffness what is the amount of information I will gain if I need to detect this specific depth of a nodule. And I basically implemented that in a control strategy. So the way it works is so the way it works is the control strategy will start with lateral sweep. So here I position randomly the probe over a region that I want to examine, and the robot will first detect where is the tissue, proceed a first lateral sweep. That will allow me to localize in two directions, X and Y, the position of the nodule based on the peak width measure and the tactile sensing. And then in the second time, we will try to estimate how deep is that nodule. And to do so, we will use what we call a Bayesian inference. So we will repeat some tests with different stiffness until we confidently estimated the depth. So we have the first sweep with one stiffness. So you can see that at the beginning the probability of being a certain depth is constant, and after that sweep, the first longitudinal sweep, the algorithm starts to define that it's more likely to be around 4 millimeters. So then we adjust the stiffness to try to maximize the information we will get to the next sweep. And basically, after the second longitudinal sweep, you can see that here, after the date, we estimate with a bit more confidence that the nodule is at 4.5 millimeters. The actual value was 4 millimeters. So we are under 1 millimeter accuracy. So here are the results. So we tested for different depth to evaluate, and basically the algorithm was quite confident with 100% detection, meaning that every time there was a nodule, we could say at least there was a nodule, and the accuracy in the depth estimation was under 1 millimeter with 3 to 10 Bayesian iterations, so meaning that we have to repeat up to 10 times the sweep. So, and if we look at the way the algorithm was changing the stiffness, so sometimes it was running 2 times or 3 times in a row with the same stiffness, because the algorithm considered that it was still gaining information by repeating with the same stiffness, but it was also adapting the stiffness from time to time to gain more information when another stiffness was more interesting to estimate. So that's one of the limitations of that algorithm is that it requires to know in advance the value of the peak force. That means that probably we already performed some palpation on this tissue, and that's a big limitation in the context of the medical application, because we might not have access to a big database of patient palpation. So I also tested based on the simulation. So I ran some finite element simulations to simulate what's happening during the sweep, and based on the force peak estimation obtained with that data, I rerun the test, not knowing the tissue that I was palpating, and the result are that it was as accurate but less confident, meaning that the algorithm was struggling more to converge to a confident value, and the probability distribution was slightly wider, so less confident on the estimation value, but still work. I will just talk quickly about the haptic phantom part, so the other part for the GP to run the palpation. And similarly, we use compliance there in the phantom. So we have basically some silicone rubber that mimics the stiffness of the liver. Then we had also some silicone to mimic the amount of skin and fat on the top. And inside, we put some rubber balloons, basically, that we can inflate with different dimension and different pressure. So basically, we can mimic the different patient conditions, some with, let's say, cancer tissues, or some different liver conditions. And the interesting part is that we could use, when we want to describe another patient condition, we just change the pressure inside those nodules, and then we keep them constant, so the GP can test. So we can use that either to practice palpation, either in teleoperation. And the interest is that once the patient condition is set, generally we have to close the valves reaching those nodules, and we can use the pressure sensors to detect and estimate where the GP has palpated. So, that's quite interesting, because here we use the same thing to mimic a condition and to measure at the same time. Which avoid, for instance, adding some sensor on the gloves, or some other sensors that may affect the palpation of the GP. So that's it for the part on the palpation probe. Now I will be switching to the part on the actuation, and I will present different examples where I think compliance is enhancing the actuation. And I will start with this project, the medical soft robots. So why do we need soft robots? Is because the clinical context for where the robots are here for surgical environment, they're still rigid, and here we have an example of the Da Vinci robot, which is a really well-known, really well-known robot for minimally invasive surgery. So basically, we have, here is a fake patient, is a mannequin, but we have the 3 robotic arm. We have some trocars on the patient, so small. They do some small incisions. They inflate the tummy with some carbon dioxide, and they can perform minimally invasive surgery with the robot. So here we have the robot, and here we have the interface in which the surgeon will sit and see with a embedded camera what's happening, and 2 joysticks to control the robotic arms. So the problem with those type of robots, in my point of view, is they are great. They allow to do amazing things every day, of course. But one of the limitations is that due to their rigidity, they might create some injuries at the trocar level or at the end effector where there is the tool. So the surgeon needs to be consistently aware of exactly where is the tool, what is happening at the trocar level to prevent any injuries to the patient. So I believe that bringing some soft robots in the medical application can be a solution to prevent that. Also, in those contexts, the patient needs generally to be sedated and completely static to prevent any injuries, because those robots won't adapt to the patient. So, in this context, we at the University of Sheffield we used to think that medical soft robot could be used for doing what we call mechanotherapy. So basically the idea would be to use mechanical stimulation to help some tissues to regenerate or just simply grow. And we have two pathologies in mind when we worked on that. The first one is the longa esophageal atresia, which is a pathology where the patients, generally they are babies because they're born this way, they're missing a piece of esophagus. So basically one way to treat that, which is very invasive, is multiplying the surgeries to basically apply mechanical stimulation to the esophagus and try to actually extend that esophagus until they are long enough to be sutured for the two pieces to be sutured together. Similarly, there are some patients that suffer from short bowel syndrome, and in that case, it's just they have a smaller intestine than usual. And a possible therapy for that would be to stimulate the intestine, so it increase the length of the intestine. So in that context, I designed the following continuum soft robot. So basically, it's composed of different layers that can be inflated, and basically, when fully retracted, it looks like that. And if I pressurize each balloons, basically we can inflate the robot and reach up to 180 elongation, which is quite long elongation for a robot. It can withstand up to 800 grams, and you can see that here, for example, the book that I put on the top was not necessarily straight, and you can see that once again the robot here will comply, and that's one of the interests of those type of robots is inside the body. We could potentially implant that, and the patient will be still able to move, and the robot will comply to the morphology of the patient. And finally, it's also possible to actuate it in different directions if we wish by inflating the balloons independently. So how does it work? How it is made is basically, as I was saying, several layers stacked on top of each other. And basically, if we have a look to one specific layer, we have some 3D printed rigid materials with a hole here at the top, another one at the bottom, and in the middle we have a rubber silicone membrane that is clamped in the middle, and we can see here some chambers. So if I inject air in the chamber, it will push the membrane, and the membrane will naturally balloon outside so a single chamber with the hole in the membrane, I call that an HBMA, for hyperelastic ballooning membrane actuator. And each HBMA can be inflated independently, so we can possibly control the orientation of and position of the robot. So during my study, I focused on the behavior of a single HBMA to try to understand how it works, proposing some models. So as I was saying, it's just a simple rigid element that clamps a membrane in the between, and if I inject air, the balloon will inflate. So part of my research is basically proposing some models. Of course, mechanical engineers knows very well how to model those type of inflated membrane, and that have been done quite a while ago. The only issue is that those models are generally quite complex, and they are difficult to be used in real time. So it means that if we want to solve those type of problems for a controller, remains quite complicated. So my approach was trying to simplify. So what I did is I simplified and constrained the geometry, and I basically proposed a very simple model that could be used for designing control strategy. I still take some properties like the hyperelastic property of the membrane here in blue, and the objective is to use that for controller synthesis or observers. So, and if I look at the result, as I was saying, here I'm simplifying the geometry. So we have the experimental test here, and if I reproduce the simulating position, we can basically predict what's happening to that membrane that is compressed. So the geometry, once again, is simplified. It doesn't necessarily match exactly what was happening, but the idea is, can I estimate the force and the position of my agent? And we can see that if we compare the experimental result with the simulation, we have some match for the pressure and the force. So it's still ongoing research in the sense that now designing the controller for the robot, and one of the issues for this type of robot in general is that in terms of hardware, most of them are controlled for the time being, regulated in pressure. But if you ever inflated a rubber balloon, you may have experienced that at the beginning it's extremely hard to inflate it, so you will have to apply very strong pressure to make to inflate the balloon, and then suddenly the pressure drops, and it's really easy to inflate it. So if you rely on pressure control, it's difficult to be accurate in basically controlling the volume of the balloon. So I would like to propose some strategies where we use the flow regulation. Okay, if I know how much air I'm injecting in the balloon, I'm more likely to estimate well its volume. So that's what I'm doing. The problem is, for those type of robot, we use quite low pressure and small flows, and the hardware available in the market, used industrially, generally way over dimension for what we need. So I propose, I'm working on that work to propose the controllers and valve dedicated for subfluids. Another aspect where I think compliance enhance actuation basically are the robotic fits. So one of the challenge in robots, in particular for working robots, is that they're not really good in working in those type of environment. So when the terrain is uneven, if it's very steep, if it is sandy or like paddy fields or wetlands where there are mix between water and mud, it's a bit difficult to bring a robot at the moment there. So we basically trying to study what's happening in the nature and what compliance can bring in those type of conditions. And so we follow what we call a bio-inspired approach. So, for example, for the wetland, we have the little egret here, that is a bird that is really familiar with wetlands and able to work in those conditions really easily. And similar, if you look here on the right, you have mountain goats, that are impressively able to work in those very steep conditions and doesn't look too complicated for them. So we're trying to understand what are the morphological properties that help them to evolve in those conditions. So for the robotic hoof, the approach is generally starting to study the biological aspect, and first we identify the links, so to propose a robotic counterpart. Then we identify the different mobilities, and generally here we have to take assumptions because those joints move in several degrees of freedom, but for simplifying the problem we decide to try to identify what is the main property of each joint, and we replicate that. And then finally, we look at the tendons and ligaments, and we model them with some springs that will bring compliance, and we try to understand what compliance we should put for each element there. So if we compare basically the hoof here and the rounded foot, which is currently what is mainly used in most of the quadruped robots like Spot or Anima. They have really round foot because it's easy to analyze and to know exactly where it is in control. But we can see that the robotic hoof is presenting this behavior. So the force needed to slide it is varying by peak, and peaks quite high. And you can see that for a bit the hoof is not moving at all, and then suddenly slipping a little bit, where with the rounded foot, the force needed to move it is lower, so it's more likely to slip actually, and nothing will stop it from slipping. So we studied basically the behavior of that hoof for different level of compliance, and the finding showed that basically the yaw angle, the yaw angle needs to be compliant. Okay, so it means that the hoof needs to kind of be able to open the toes, and the roll is needs to be stiff. So the motion in that direction should not be too high. And basically, if we analyze the type of motion, it's a bit like when someone is trying to brake while doing some ski. So basically, the yaw is kind of flexible and stiff angle with the so, basically, that shows that choosing well the compliance of the foot is can help reducing the slip of robots. Similarly, we are currently with my PhD student investigating about the quadruped aspect, and we're studying egret bird foot to try to understand how they adapt to those mixed environments, mixing mud and possible water, and how those type of feet comply to this environment. And the idea is to reuse a bit the same concept as for the palpation probe, but expand it to multi-phalanges fingers and toe, and basically be able to change the compliance to see how it helps to work in those environments. Finally, the last example for the enhancing the actuation I will provide is about a collision-safe robot joint. And the context of this project is something we're running with some colleagues at University of Sussex, and it's in the context of the nuclear decommissioning. So the issue with nuclear environment is that there are obviously radiations, and radiations are basically damaging the senses mostly. Okay, due to the radiation, most of the components are sensible to the radiation, and we can't necessarily use standard sensors to bring in the nuclear environment. So it also brings some noisy signal as well. So, but we still want robots to be able to interact with the environment in a safe manner. So if we can't put more sensors to detect the environment, can we solve that problem using compliance and mechanical aspects? So it's what we did, and basically we propose a solution based on the CVT, continuous variable transmission, and the idea, to make it simple, is we have that CVT, which is a transmission between the motor we will be using and the robotic joint, and basically if we have an obstacle and the robot hits the obstacle, the transmission will vary, and basically the motor can continue running, but the transmission will detect mechanically that there is a collision and stop the joint from running further. So if I zoom a bit in and explain a bit how it works, is here we have what we call toroidal CVT. So we have some different discs connected with a ball, and basically if I spin this toroidal disc, it transmits basically the rotation out to this output disc by friction here. Okay. So if I apply an external torque from that side, what will happen is we have a force torque coupling here. It will push mechanically the disc on the left and push also this disc a bit more on the left, and it will change the ratio of transmission of the CVT. And if at some point the output torque exceeds a certain value, the transmission ratio will even fall to 0, which means that the motor can still continue spinning where the output is actually stopped. And we have a pneumatic cylinder here to apply a constant pressure at the toroidal disc level. And by changing the value of force that this pneumatic cylinder is applying, we can change at which torque basically the output will stop. So basically we have an element that makes a collision safe robotic joint. And the possible application for that technology that we are currently investigating, we are building 2 robots basically. The first one on the left is more for scenarios that could apply to Sellafield, for example, in the UK, where there are some rooms in which there are ports which can bring to the radiated environment, and they want a robot that could probe, test the radiation in that room at different places. So by adding the CVT transmission at the joint, we could evolve in that environment without damaging too much whatever is inside the room. The second scenario, and we're investigating, the project is in a partnership with the University of Tokyo, and they are interested in using the technology for a robotic manipulator to basically clean the damaged units in Fukushima Daiichi nuclear power plant. So basically the pressure vessel is damaged, and some fuel is melting, and there are some kind of pebble-like really high radiation material that needs to be picked and stored safely to be brought out of the vessel. So my contribution to that project is mainly studying the behavior of the compliance of the CVT in those collision, but also I use my expertise in impedance controller and variable impedance control to basically simulate the environment condition. So we test just the motor and the transmission, and we use a second motor that would simulate any collision, any relation between the robot and the environment, so to perform a kind of hardware in the loop system. That brings my talk to a conclusion. So as I already mentioned several times, what I would like you to bring home is that the compliance is a very interesting element to study for robotic, and in particular it can affect the way they interact with human or with the environment, and they have a role not only on the actuation, which is quite obvious at the beginning, but it can also help to filter or change the perception of the robot, and sometimes simplify, filter the unnecessary information from for the robot. And it needs to be taken into account when we design systems, in particular the position of the sensor or the interactive part of the robot or the expected reaction to the distance needs to be considered when we want to study the compliance of the robot. In the future investigation, I'm really interested to develop some more soft robots for medical application, and in particular I have in mind some rehabilitation of prosthetic devices. I'm currently running some studies to see how the compliance affects the energy efficiency of robot, because compliance is also a mechanical way to store energy. So for locomotion, for instance, it can be interesting to store it, release it when needed. And finally, I would like to study the impact of compliance on observability, following that it can filter some information. Can I develop the observers, so the control with the control approach? I mean, observers like virtual sensors based on control theory, using the compliance aspect. So I would like to acknowledge all the people who have been involved to that work. Of course, I presented a lot of things. I'm not the only one working behind that. And specifically, I would like to thank my colleagues at the University of Sussex, my postdoc supervisors in Sheffield or at Imperial, as well as all the collaborators that have been working with so far. The clinicians, because several applications I've been working on are on the medical field, and without them we couldn't have any data or any feedback on what we design. The industrial that are sometimes in the loop of certain projects, and of course the funding bodies, the Royal Society, the UKRI, and the French research agency, which made all that work possible by funding it. And I would like to thank you for your attention, and I hope you enjoyed the journey throughout robotic compliance. Thank you very much.
Thank you, Nicolas. I mean, a very wide-ranging talk, so I'm sure there are some questions amongst people. Who would like to start? Yes.
The example you gave of a robot for elongating an esophagus, for example, how would that actually work in the esophagus? How would you sort of grip it and then extend it without blocking it?
So basically, some tests, not for this design, but another design a bit more rigid, actually, using simpler element have been tested actually on pigs in that sense. So that was work from my postdoc supervisor in Sheffield, and basically the way that they did is you need the first surgery to implant the robot. But the advantage is compared to the standard method where basically they for the esophagus the method will consist in sedating completely the patient, so the patient is not moving, opening, getting some strings out of the body in the way it was possible, and pulling regularly, manually, to help growing the tissue. So very invasive, the patient can't move. For the context of the pig, when it has been tested, basically the robot was inside, and the pig was, after the surgery, was awake with the element inside the body. And since those type of robot can comply, it's difficult to ask a pig, obviously, but it seems that the pig was able to move, to do any activity as usual. So yeah, the way it would work is implementing first through a surgery the robot, then leaving it. In the context of the pneumatic, we still have a difficulty to solve, is how to bring air inside, because we still need to bring air and release it as well. It can't be stored indefinitely in the body. But we have thought about different solutions, and like for electricity, the battery was actually attached to the back of the pig. So of course there's still some constraint that still need to be solved for miniaturizing the implants and bringing them, bringing all the energy source inside the body, but it's still something we're working on.
But the example that you gave with the inflating balloons that sort of elongate, how would you actually attach that to the esophagus? Because if it goes inside, then it's blocking it, isn't it?
So we've been investigating by different attaching methods actually, but that's not necessarily my work, but some students investigated. So the first one is just simply suturing the robot, so the two extremities, suturing them to the esophagus. Now we also investigated different surgical glues, which are promising, and there are some also other materials which are a mix between how to say, it's a mix between fabric and biomaterial that can also help to attach the robot to the thing. Now those new material, the complexity is here none of the material I've been using were really biocompatible. Okay, so because we're still at the conceptual level, now most of the material biocompatible are extremely expensive, and they need specific manufacturing process to remain biocompatible. So that's actually part of the next study, but performing preclinical trial is something very long. It takes many years to have the approval, to have the right to test correctly. So that's why only the previous version has been tested for so far preclinical trial. Still waiting for the next campaign of tests with new technology.
Doesn't it block the esophagus if it's inside?
Basically, I can come back. Is something we thought, and so there are different ways to do it. But what we thought is either we do the robot bigger and we attach it to the external part of the esophagus, and the esophagus would be in the middle. Another approach would be inside, and you can see that there is a hole in the middle So potentially the food could still go through. Anyway, to be honest, since they're missing the esophagus, they don't eat any solid food or even liquid food. They feed it through veins directly because it's really complex pathology. So food passing while the robot is there is not necessarily a big concern for the esophagus. For the case of the short bowel syndrome, it's more likely that they would be allowed to eat, but we expect that with the whole, maybe liquid food. Yes.
I'll just ask a question, if I may. In the high radiation areas, you say that the difficulty is that the sensors degrade in that environment.
Yeah.
But you're using sensors, so how do you manage that?
We can't remove completely the sensors. The idea is trying to reduce the number. For example, for most of the stiffness control or impedance control, we need to add a force sensor, for example, either at the end, but in that context, we will need several sensors on the links as well to detect what's happening. And yeah, so we still have, for time being, we still need at least encoders, for example, which can be affected by the radiation. Now, they design some sensors that are called hardened to go in radiation environment, but they still have limited lifetime and limited. They're still sensible to noise, but there are some solutions. Our objective is to reduce the number of sensors we need to add to our manipulator.
Any other questions? Yes, Mike.
I was interested in the detection of nodules and you know, making it safe by getting the compliance right. But the question is, how much better is a good robot than a doctor doing the same thing?
In the context of my research, the idea had never been really to remove completely the GP from the loop. I'm working actively on medical robotics, and I think that ethically it's complicated to say a robot would replace a medical decision. Now, how good the robot was to detect the death, I think it depends. Probably really experienced surgeon would be able to estimate the death quite accurately, but it's not something they train too much to do so. And in particular, if we switch to the minimally invasive context, sometimes the surgeon even don't have access at all to those type of tissues. So that's where.
So it depends on the training of the surgeon as well. You know, a good surgeon will be better than, but a robot would be better than a poor or a learning surgeon, or maybe would the idea be to use them both together, or would the, you know, how far will you be able to automate, or is it always better? Because a surgeon gets tired, a robot doesn't.
Yeah.
You know, is it best to have them both together or something?
Yeah, I think we're still at the stage where robots and surgeons should work together. Most of the surgeons are really robotic enthusiasts because they like the fact that we reduce invasiveness, we reduce the. Sometimes with those tools, they suppress any parasite motion from the surgeon, so it allows to be much more accurate, much more precise. They like that aspect. They really like that aspect. Now, yeah, I think robots and surgeon should work together. Now, for the depth estimation, there are also some other tools using imagery that can do the same thing. Now, the problem of some of those tools are, for example, if you're using X-ray, it's not really good to expose too much people to X-ray for too long. So it's just a different approach. But I doubt that palpation will be ever the most accurate way to determine the depth. Now,
but would it be in combination with, say, ultrasonics or something like that?
exactly. So that here we would reach a kind of sensor fusion, which I was already investigating with the tactile aspect and the kinesthetic aspect.
Combine the detector with the sensor.
Exactly. So I believe that by mixing the number of sensors, yeah, could reach something maybe non-invasive and very accurate. But yeah, the idea here was really to also understand how palpation works, how it is performed. Because when you talk with surgeons, they're doing those gestures every day. I don't know if you ever notice also the way sometimes they tap to perform some diagnostic. It's extremely hard to ask them, what are you measuring there? Because they've been doing that thousands of times, they know exactly what to expect, but they're not able to explain physically what they're doing. So we're still in the process where we learn from their gesture, we're trying to interpret what's happening and give some sense. So our hypothesis, once again, there was probably compliance is playing its role, and this is how we explain compliance could impact the thing, but it's still the scientific aspect to try to understand those techniques, and can we mimic them through engineering.
So there may be a role for artificial intelligence with that. Yes.
Very certainly. I mean, Bayesian inference is widely used in artificial intelligence as well.
Yeah.
We talk a lot about deep learning nowadays, but it's not the only way to do AI. So Bayesian inference is definitely one.
Anything more? Well, then perhaps I'd like to ask you to join me in thanking Nicolas for quite a stimulating talk and quite wide-ranging area. Certainly, I wasn't aware that that work was going on. So please join me in thanking Nicolas.